The so-called facility location problem will now be used to introduce to you the notion of aggregated and disaggregated formulations. The story goes as follows. Imagine that there is a set of M locations where you could open a facility to serve some or all of N customers. Each customer has a certain demand, and Cij is the cost that is incurred if the total demand of customer J is met by a facility at location I. If a facility is opened at location I, there is a fixed cost of Fi for doing so. There are two things we have to decide upon, and a corresponding set of decision variables is straightforward. First, what percentage of the total demand of a customer J is met by the facility at location I? And second, shall we or shall we not open a facility at location I? The question is, how can we meet the demand of the customers in the cheapest possible way? As always, I recommend that you try to model the problem by yourself and pause the video now. Let's start with the objective function. Our goal is to minimize the total cost. There are two types of cost. If we meet the total demand of customer J by the facility at location I, the cost would be Cij. If only a fraction Qij of the total demand of customer J is met by the facility at location I, the cost is Cij times Qij. This applies to all combinations of locations and customers. In addition to that, we have a cost Fi if we open a facility at location I. The constraints we have to care about are the following. The demand of each customer must be met. In other words, each customer must receive 100% of his or her demand. A customer can be served from one facility exclusively, or the customer can be served partially from different facilities. Formally, this looks like so. It should be clear that service by a facility at location I can only happen if there is an open facility at that location. Mathematically, this can be couched as follows. If xi equals 0, no service can be provided at location I. If xi equals 1, no more than 100% of a customer's demand can be provided by the facility at location I. Note that, due to our choice of decision variables, this constraint is as simple as is. Qij was defined to be the percentage of customers' j total demand, and therefore its value is between 0 and 1. If we had defined Qij being the number of demand units that are delivered from facility I to customer j, then we would probably see a big M formulation here, as discussed in a previous video. I leave it to you to formulate an alternative model where Qij is given in absolute terms and not in percentages. As a hint, you should introduce an additional parameter, say dj, to denote the total demand of customer j. Coming back to our model, we shall not forget the domains. Now this is a complete and correct model for the facility location problem. But we can derive an alternative formulation from that. Look at the constraints shown in red and notice that we have n less than or equal to constraints for each location I. If we add up all the constraints that belong to the same location, we get the following. Leaving all other components of the model unchanged, we get a new model for the facility location problem that is correct as well. Make sure to understand that the two models are equivalent. In the new model formulation, if xi equals 0, as before, no service can be provided at location I. The situation for xi equals 1 is slightly more complex to understand. The new constraint shown in red states that if xi equals 1, the service provided at location I cannot exceed n times 100%, which sounds a bit strange. What makes sure that for a location I, a value Qij cannot exceed 100%? The answer is that the first constraint, in combination with the domain of the Q variables, guarantees that all Qij's have a value between 0 and 1. Note that the new constraint shown in red works very similar to a big M formulation, which was explained in a previous video. The first model formulation is called a disaggregated formulation, and it has M times N coupling constraints that link the variables Q and X. The new model formulation is called an aggregated formulation, and it has just M coupling constraints that link the variables Q and X. One could therefore think that the aggregated formulation is better because it has less constraints. But things are a bit more complicated and can only be fully understood when studying solution procedures, which is out of the scope of this video series on modeling. Just to give you a hint, if you ignored for a moment that the X variables are supposed to be binary, you could again compare the disaggregated and the aggregated models and would see that out of a sudden the two models are not equivalent anymore. Consider, for example, that each of the x's equals 0.5. Assume also that we have at least two customers. In the disaggregated model, none of the q values can be larger than 0.5, but in the aggregated model, the right-hand sides are n times 0.5, which is at least 1, and therefore one of the q's on the left-hand side could be 1. In summary, the solution space of the aggregated model is larger than the solution space of the disaggregated model if we consider continuous variables. This phenomenon is the reason why a disaggregated model formulation is often considered to be a stronger, if not better, formulation.